Okay, it's recording now. Just for those that don't know me, I'm Philip Sheep. I manage the AM2D Research Hub, and I just want to very, very briefly just say that this is our first talk for the year, and thank you for joining us. We have a whole host of events coming up this year that you might be interested in. I'm going to put my email address in the chat, so please send me an email if you want to be part of our mailing list. Otherwise, enjoy the talk. And very quickly, I'm just going to do the greeting. AM2D and Monash University place in which to acknowledge the people of the Kulin Nations on whose land we are gathered today. We pay our respects to their elders past and present, and I ask all of you to pay respects to the traditional owners on the lands which you are situated. Monash, please, over to you.
Thank you, Phil. I think it gives me great pleasure to introduce Professor Yulin Zhong. So Yulin just became a professor this year, so congratulations, Yulin.
Oh, thank you.
I know him from his research fellow days at Monash University. So I'm very proud of what you have achieved. So brief biography. Yulin did his PhD at the National University of Singapore. Then had postdoctoral training at Princeton University and MIT. And then he started a DECRA fellowship at Monash. And then in 2016, he started his own career at Griffith University as a lecturer. And he has been awarded several fellowships, DECRA, ARC Future Fellowship, and his research area are in the domain of electrochemical production of 2D nanomaterials.
Yeah, it's probably getting pushed back again, isn't it?
David, can you mute yourself? All right. Without further ado, I provide the stage to Yulin for his talk. Thanks.
All right, thanks. Thank you, Manek. So I'm not very familiar with Zoom. I'm just trying to share the screen now, and hopefully it should work. I guess I share this. Yeah.
We can see it.
Okay. How do I? Okay, I'll move this aside. And then I should press on.
We can see your screen, by the way. All good.
The screen is good?
Yeah.
Okay. All right. Thanks. So thank you. So it's all looking good. And can you see my mouse? Are you able to? Should I change it to a pointer? Or pointer? Yeah. So it's all good.
Yeah.
Oh, thank you. Thanks. All right. Yeah. Again, thanks. Thank you, Manek, for this invitation. And yeah. So it's been decades that we've known each other, and but it seems like yesterday. Manek, you still look the same. All right. So thanks, and very, very honored to be presenting it to this Talk2D series. So basically today I'm just sharing my work on electrochemical engineering and also bit of 3D printing. And also, basically my research in Australia. So first up, oh boy, yeah. So okay, great. So just a brief introduction of Griffith. Welcome to visit us at Brisbane. So basically, we have our first campus at our foundation campus at Nathan, and nowadays we call it South Brisbane Nathan. So that's our first campus, and we are celebrating our 50 years anniversary. And I think there'll be lots of celebration throughout this year. So do welcome and enjoy our celebration. We also have another big campus, and actually the biggest campus at Gold Coast. And I was fortunate to spend 5 years of my time there. So please do visit us. And the other news is that we are expanding across the river. So we are buying or leasing this iconic treasury building in the CBD area. And yeah, that's sort of expansion of Griffith into the CBD area. And yeah, do welcome to visit us whenever you're free. And so at Griffith, I lead this energy materials research lab. It's currently in this N44 building. And in this lab, we have all the typical stuff: glove box, argon glove box for lithium-ion battery research, a nitrogen glove box with a evaporator there for solar cell research. So I share this lab with a couple of other colleagues, in particularly Mugi, who is the expert in solar cell, and also a relatively newer colleague called Sina Jamali. He's an expert in electrochemical sensors. So we share this energy material research lab together. And yeah, we'll have all the standard material characterization tools, battery testing, and more importantly, we have 3 different type of 3D printer: the typical FDM type, the SLA type, and the BioX, which is the direct ink writing type, which I will focus more on. Yeah. So my research in Australia started sometime in 2013 when I first got the DECRA ARC DECRA fellowship. So the first project was on this, of course, making graphene using electrochemistry. And then subsequently, 6 years later, I got the future fellowship, and then extending this electrochemical technology towards producing other types of 2D material, including MXene. And then concurrently, I've also dabbled with the use of the 3D printing. So in the first DP is on understanding the chemistry of nanocomposite when it's extruded through this printing process. And then we go towards fabricating devices, strain sensors, and also, more importantly, currently focusing on wearable batteries. So I guess batteries is of great interest to Manek and also Ashok and lots of you here. But I'll say that I'm not a battery expert. I collaborate with the battery expert at Griffith, and also experts like you guys. So yeah, so the nanomaterials that we produce can very well be applied or used into batteries straight away. So the graphene or MXene that we make, we put it into as used in supercapacitor, mix it a bit with other active material, put it into ion batteries, lithium-ion batteries, lithium sulfur, sodium ion, aqueous zinc ion batteries. So these are the type of battery technology that we have. We have tried and found that we could. So I'll share a few examples that we could make use of the unique functional property of those nanomaterials that we produce, and how they improve the battery performances. So at the same time, if we were to create wearable devices, then we will need another tool to help us. And then in this case, we would make use of the 3D printing technology to fabricate the devices of the nanomaterial that we produce. So I think in the talk today, I will just talk to you about the direct ink writing 3D printing technology, which is very suitable for chemists to fabricate the devices. So of course, one of the main area is on wearable energy storage. And we are also just getting started on this nano generation. So there are 2 types, the triboelectric and also the piezoelectric. And this would we see that it will complement the energy storage and also because of the fact that it's a wearable device, there will be movement, and so a nano generator will be ideally very suitable to generate the electricity and then having the wearable battery to store the energy. And of course, for wearable device, then the application would have there are lots of application. So we worked on strain sensing, strain sensors, and then currently think we're really, but it's also in collaboration with other colleagues on sweat sensing. So those are the wearables sensing or sensors or application that we are working on. So yep, so that's just an overview of what I'll be talking today. So let's start with electrochemical engineering. So this is not something that's new, and I always give this prime example of aluminum, which has been around for decades, and we refine aluminum using electricity, using electrochemistry. So putting aluminum oxide in this electrolysis reactor and passing electricity, and end of the day you get pure aluminum. So this electrochemical engineering to produce commodities or materials is not new. And so in our research, we want to capitalize on this electrochemistry and produce functional nanomaterials, and also different types of other nanocomposite materials, which we could directly use in the application that I've spoken about. So in the very beginning, we just use electrochemistry to basically exfoliate graphite into graphene. So the basic concept is you just apply. Of course, the electrochemistry is very much different from the aluminum refining process. Well, it's much simpler. We start off with the graphite as the electrodes and apply charges, and that would encourage intercalation of ions, and that would cause expansion of the graphite lattice. And what we can do subsequently is also apply electrochemistry to functionalize the expanded graphite, and then exfoliate to obtain the functional graphene. So this electrochemistry or electrochemical engineering is a powerful method for us to design and get the unique functional materials that we want. And then there are several advantages. You can just think about the energy that you put into the reactor. I think we can control the amount of energy or the electrons that we put in the reactor, and all the electrons we could potentially target it to do the reaction that we want. So this is a very energy and cost-effective process compared to traditional reaction where you just heat the whole vessel up. So in terms of energy and cost, this is potentially a very effective process. And you see that in my example that we can reuse the electrolyte again and again, and so this would minimize chemical waste. So it's also a green and clean method. And yeah, there's a whole lot of a field of electrochemistry that we can apply and make the material even better. So well, this work is 13 years old. So but basically just to show you that we have done the graphite expansion, exfoliation, functionalization all before. And just want to point out that in the past, what I did was I employed this graphite material as a starting material, and this graphite material is a graphite foil. So graphite foil is made up of expanded graphite. You get a graphite intercalated compound, you expand it, and then you calender it and make it into graphite foil. So it's kind of a processed and expensive starting material. But anyway, that was the material that I used in the past. And in the past, I've written that we use the graphite foil, but before using it, I have to reduce the thickness down to very thin, 0.5 mm. And that was in 2011, 2012. And then a few years later, there are also other reported papers that also made use of a graphite foil. And yeah, that was in 2017, 2018 where they also said that they employed graphite foil in their electrochemical exfoliation. And also you notice that they use the thickness of 0.5 mm, similar to what I've used. So I would just say that there's the reason that we had to use such a thin graphite foil is because of the reproducibility, the scalability. So the reaction, the electrochemical reaction, if it were to be done on a thick electrodes, then there's a issue with getting the reaction, getting a complete reaction such that we get down to a single layer graphene, functional graphene. So this is the thing with thick electrodes. The reaction might be not so uniform, and we might end up with multi-layer graphite instead of a single layer functional graphene. So that was the problem that we realized long ago, and so that's why we had to come up with a new method to overcome this challenge. If we were to really have a good electrochemical reactor that is scalable and reproducible. Yeah, and the other obvious reason is graphite foil. You can see that the cost is 100,000 a metric ton. So that is like 100 times more expensive than flake graphite. Anyway, this price is I think the prices would be more expensive now, but the fact is still that the graphite foil would be much more expensive compared to flake graphite. So when I started in Monash 2013, 2014, that period, we thought of that we can't just simply use graphite foil or graphite electrode or preform a graphite electrode to produce graphene. That's not going to be scalable. So yeah, as a chemist, we thought of just a simple method to have a very rudimentary reactor. So this reactor, you can see, is made up of a chemist glassware. So we have a bigger flask outside, and in the middle we have a glass tube. And at the end of the glass tube, I would just cap it with a porous membrane. And inside the glass tube, I've lined it with a titanium mesh, which I connected to a platinum wire and use that as the working electrode. So the counter electrode is simply another platinum wire swimming about, sitting around in the outer cylinder. So you can see that it's really a rough reactor that I made a long time ago. So the idea was that we can then put in the graphite flake and then have a stirrer in the middle to agitate the graphite. And whenever the graphite come into contact with the working electrode, it will then get punched with electrochemistry. And well, it sort of work. And so we are able to transform flake graphite in this reactor into what we call the electrochemically derived graphene oxide. So I think we are the sort of the first group that point this term electrochemically derived or produce graphene oxide. So we made graphene oxide using electrochemistry. And you can see that it's just in, a benign electrolyte, just saturated ammonium sulfate, a neutral salt, and then acidify with 1 mole of sulfuric acid. So pretty safe compared to the Hamas method, graphene oxide. So we also reported on I think an important point of this graph EGO. So we observed that it is able to undergo a thermal conversion from its insulating form when it's being synthesized to its very conductive form by just a low temperature annealing. So you can see that its sheet resistance increase to its very conductive form at just 200 degrees Celsius. And we show that in later paper that just 150 degrees Celsius is also possible to do this conversion. So in comparison, it's impossible for Amos GO to be conductive with such a low temperature heat treatment. Yeah, from XRD you could show that the EGO really transformed from a GO peak to its graphitic peak at this 200 degrees Celsius. Well, so I would say that for this mechanical assisted production of graphene oxide, this is something that has a big potential. Yeah, because so it could be designed into a continuous process. So imagine you have this reactor and you have your graphite coming in at one end and undergo reaction and just speed out the other end. So this mechanically assist electrochemical reactor could be engineered into a continuous process instead of just a batch process. And yeah, but unfortunately I'm not a mechanical engineer. I think need to have collaboration with Manek and other mechanical engineer to realize that. Well, so as a chemist, we like to keep things simple. So we want to study the electrochemistry that's occurring. So that's why we employed this T cell. So it's a T cell made up of a Schwarzschild connection. So it's also frequently used in electrochemistry, and it's very simple, just having one side as a working electrode and the other side the counter electrode, and separated by a separator. And in some case, we would also insert a reference electrode at the top. So we just want to study in this paper. We just want to study the what's happening when in this electrochemical process. So we could then apply a constant current and look at the potential of the cell on how it changes. So from this charging curve, we can clearly see that in the very initial stage, the graphite is being intercalated with in this case chloride ions. So it's like charging like a supercapacitor or batteries. So that is what's happening in the first stage, and then it's followed by a longer stage. If you leave the reaction to go on, it will. The first stage intercalated compound would then be oxidized into what we call the graphene, the electrochemically produced graphite oxide. And the nice thing about this electrochemical reaction is it is self-limiting. So after the complete of the reaction, we could see a spike in the cell voltage, and then that would tell us that okay, now the electrode is just bleeding water. So it tells us exactly how much charge that is required to put into the reactor to oxidize the graphite into graphite oxide. So that's the nice thing about this electrochemical reaction. And also we can simply control the electrolyte concentration. And in this paper we found that at electrolyte concentration of 9.2 molar or lower, we could predominantly produce a graphene or graphite oxide with just a single bond, basically just hydroxyl or epoxy group. So these are all C single bonded to oxygen. And if we were to increase the electrolyte concentration, and that would increase the oxidative power, and then we would then start to see the formation of a carbonyl group, which is in this case in around 11.6 molar. So that's demonstrate that we could easily tune our graphene material by simply choosing the right electrolyte concentration. So of course, there are also many other parameters that we can play with, different types of electrolytes, chemical additives, even the charging. So if you were to keep on applying a positive current, that would oxidize. But if you were to apply a negative current, then that would potentially reduce the graphene oxide in the chemical in our reactor. And also we have a student who focus on the design of this electrochemical reactor, and we do that using 3D printing. So this is the very first version of our packed bed electrochemical reactor. So yeah, so that's why we, as I mentioned, it's really difficult for us to pursue on the mechanical or the continuous reaction. So as a chemist, it's easier to focus on the batch reaction, and so we end up designing this packed bed electrochemical reactor, where we put in the graphite in a reactor, and then we packed it with a plunger from the top, and the plunger would compress the flake graphite onto the working electrode. And in this case, we make use of a diamond-doped electrode as the working electrode. And of course, the reason for that is diamond is resistant to acid. It can also afford a higher working voltage. So the water, so it has a so the water doesn't split on diamond electrode until above 2.5 or 3 volt. So that's the nice thing of selecting this diamond electrode. Then along the way we modify and upgrade the reactor, and in this case we have a place to insert a reference electrode. We also make use of a glass tube as the house of the reactor, and this is to let us look at what's happening to the graphite as the reaction proceeds. So these are just some modification or improvement for us to understand the process better. And this is the kind of the current design right now. Still, you see that the boron-doped diamond is at the bottom, and we have the graphite pressed onto the working electrode, and then we have a glass tube that allowed us to observe what's happening, and the counter electrode is simply platinum wire. So in this paper, we demonstrated that we could, in this packed bed reactor that we designed, and we could do a similar type of electrochemistry. And in this in this paper, we looked at using sulfuric acid, which is of course cheaper than perchloric acid, and it does the same thing. It oxidizes the graphite well and transform it into graphite oxide. And through 3D printing, we are also able to scale up the reactor to produce a few grams of graphene or graphite oxide. So just some characterization to show that we indeed produce graphite oxide. So similar as the graphene as the graphite oxide produced using Harmer's method. So we denote it as chemically produced graphite oxide. So you could see that in solution, the EGO appeared to be darker compared to CGO, and that's got to do with the lesser degree of functionalization. So the oxygen functional group is probably about 70% compared to Harmer's method, which is 60%. And from AFM, SEM, you can see that we can get down to predominantly single flake EGO, and the size of those EGO are about 1 to 10 microns. And I would say that this size is because we have to go through during the washing step, we have to go through ultrasonication, filtration, and centrifugation and ultrasonification. So during the ultrasound or the washing step, the size could be bigger initially, but it got reduced during the washing step. So we shown that we can scale up the reactor by just using the 3D printer that we have, and we are only limited by the size of the 3D printer that we have. So the biggest size the biggest reactor that we produce is this about 100 with the base area of the base area of a 15 centimeter diameter. So we have successfully produced up to 60 to 100 grams of graphite oxide each time using this reactor size. So if you were to scale up just laterally, if you have the base diameter of 1 meter, then probably could start getting kilogram scale. But again, this reactor is, I would say, it needs a lot of improvement. So we are working on that. So one of the other improvement that we need to make is to improve the electrolyte flow. Because of this packed bed setup, it's pretty hard for the electrolyte to penetrate down to the bottom of the graphite packed bed. And in particular, if you were to use an expanded graphite instead of flake graphite, for expanded graphite is of course very loosely packed, and it takes up a huge volume. So it's a long way down for the electrolyte to go. So in this, so we overcome that by just adding this porous tube, porous pipe. We call the irrigation pipe to allow the electrolyte to flow all the way to the bottom and have a good penetration of the electrolyte into this expanded graphite, which we use as the starting material. So in this paper, we simply did this modification, and we are able to oxidize expanded graphite into the EGO that we produce, and then we just simply take the product and use it in as an anode in sodium-ion battery. So the thing with this is we need to control the oxygen functional group on the product. So if we were to use the as produced graphite oxide, it's not that good. But we can do a bit of annealing to improve the conductivity. So we did try a series of annealing, and we found that by annealing the graphite oxide for just 20 minutes, it gives us an optimum product with a good conductivity and also some residual oxygen functional group that keeps, I think, the graphite interlayer spacing big enough for ions to penetrate. So that's the thing. We could do some small modification to the product and to make it better. And for this example, it's used and directly used in sodium-ion battery. So in the next example, we mixed it with vanadium oxide. So vanadium oxide, I think we are all familiar that it's a good material for zinc-ion battery. So in this vanadium oxide water dispersion, we just simply add our EGO in it, and then we put it through a spray dryer. So in a spray dryer, we set the nozzle temperature to be around 200 degrees Celsius. And remember, at 200 degrees Celsius, it will thermally convert EGO into its conductive form. So by simply adding our EGO and then having it go through this one-step spray drying process, we could get a amorphous vanadium oxide EGO composite material. And then this is a good material for zinc-ion battery application. And of course, it has to be the right composition. So at a composition of, I think it's this one over here, we could get a really high zinc-ion battery with really good energy density, and also comparing to other work, is doing pretty good up here. So this one of the first example or that in a zinc-ion battery application. So let's switch gear a little bit to another 2D material that is MXene. I think Manek and his group is also in this area. I've seen lots of papers of Manek group on MXene and energy storage application. So I'm also about quite late into this view of MXene. Yeah, I think we only worked on it in starting 2016, no, it has to be 2017 or 18 or even later. So by that time, MXene has been around for, again, more than 10 years. So we were late on the graphene bandwagon. We are also late on this MXene fashion. But well, for MXene, what's so nice about it is because it can be oxidized, and yet it retains its electrical conductivity. So unlike graphene oxide, which is insulating in its oxidized form, yeah, MXene is still conductive in its oxidized form, and so it's you don't have to reduce it, or you don't have to go through a lot of trouble to make MXene conductive again. So that's, I think, the unique advantage of MXene. But similarly to GO, the synthesis of MXene is not it's a bit difficult. So but it's not as difficult as GO, where Hammer's method is explosive, is inherently explosive and dangerous. Well, but to etch MEX into MXene, you need HF. You need hydrofluoric acid. So yeah, in many university, we need to go through lots of risk assessment to be able to use HF. And I think in some university they even ban researchers from using HF. Well, there are ways to I think mitigate that. So one way is to produce in situ generated HF. But still you're making HF, and the toxic risk is still there. So what we did was we employed our electrochemical reactor, and of course the chemistry here has to be different. And in this reactor, we use the electrolyte of just ammonium fluoride. So ammonium fluoride is a neutral salt. So it doesn't, well, there's no HF in it, as long as you keep the pH neutral or and above. If you were to add a bit of acid to it, then of course it will generate HF. But as long as we keep the pH above neutral, there shouldn't be any HF. So that's the electrolyte. That's the electrolyte salt that we employ in this etching experiment, in this etching. So basically, it's just an electrochemical etching of MEX. Using the fluoride to react with the aluminum and to remove the aluminum. So the first optimization we did was looking at the electrolyte concentration, and we found that well, there needs to, and these are the charging curve of the reaction. Yeah, and these are the XRD of the product that we obtain. So we found that there's a optimum level of ammonium fluoride concentration. So it has to be at least 6 mole for us to get the MXene. So if it's not too constant, if it's less than 6 molar, then the etching process is not that good. And we can also see from this, from the U, we get good U only about if the electrolyte concentration is above 6 molar. So that's why we chose the about 10 molar of HF of ammonium fluoride concentration to proceed. So in this, you would think that well, it might be just due to thermodynamic. Yeah, if you have a sufficient reactants, then the reaction will proceed. But there's an interesting story to this. So the other thing, I think I won't spend too much time excuse me, explaining is the kinetics. So there's a limit to the high current that we can put into the reactor, and of course beyond a certain current density that we put in the reactor, the reaction doesn't go that well. as evident from the parent peak, the parent max peak. So this is simply due to kinetics, the way electrolyte penetrating and reacting and etching. So we can't force the reaction to go too fast. So to overcome that, then we have to redesign the reactor. So in this example, we just show that by expanding or increasing the reactor size, then we can get higher production rate. But of course, there's we have to do better to improve the kinetics. Well, just to show some characterization data that we indeed are able to etch away all the aluminum. The aluminum get etched away, and so we get MXene by etching away the aluminum in MEX. And we can also get down to I think 1 or 2 layers thickness of MXene, as seen in the AFM here. So yeah. So the nice thing about this electrochemical method is that we could reuse the electrolyte, the ammonium fluoride. Yeah, remember, I just simply use ammonium fluoride, 10 mole ammonium fluoride, and we could reuse that over and over again, up to over 5 times, and we get the similar amount of U of MXene. And the nice thing is we could even replace the diamond electrode with graphite electrode, and that is because of the etching potential. So the etching potential of MEX to MXene is less than 1 volt. So you could see typically it's less than 1 volt. So in such a low etching potential, you don't need the diamond electrode, and it's a neutral electrolyte, so it doesn't really harm the electrode. So we could simply replace diamond electrode with graphite electrode, and it still works the same for 1 gram, and in this bigger reactor up to 20 grams. So we could produce 20 grams of MXene each time in our this reactor. Well, so the reaction mechanism, as I mentioned, uses the fluoride and undergo 3 electron process to etch away the aluminum and to form the side product, the byproduct, aluminum fluoride, and you ended up getting the MXene here. But it's very strange that we observe that. Well, we have to use ammonium fluoride, and if we were to change it to potassium fluoride, the reaction doesn't work. So this is a very strange, because from the reaction, you just think that it's just a fluoride participating in the reaction. So why does the cation play a role? So this is very strange that potassium fluoride doesn't work. And then the other observation that we found in our reaction is the max. Yeah, from starts it is this thickness, and over the time it gets expanded. And from SEM of the product, we can also see that the max get expanded. So this really telling us there's a gas that's being evolved that makes this max. Although just the aluminum is being etched out, there's also a gas evolved that pushes this max apart to create this accordion-like structure. And so we decided to separate the reactor into 2 components. One side we have the max, and the other side is just a platinum counter electrode. And in this separated reactor, we then test for the gas that's evolved, that's coming out from the max during the reaction. And the gas is something that changed the litmus paper blue. So from high school chemistry or undergraduate chemistry, we know that it has to be ammonia gas that turns litmus paper blue. So this is then very strange, because we don't expect ammonia gas to be produced at the working electrode, because we are putting positive charge to the working electrode. So why would ammonium fluoride, the cation, come to the working electrode? So that's very strange. That shouldn't occur. And also at the working electrode, at the positive electrode, this reduction process wouldn't occur. It's a oxidating process, not reduction. So we have to go back to again high school chemistry, and we recall in high school chemistry about solubility product. So for ammonium fluoride, its solubility product is very low. It's only 44 compared to potassium fluoride. So the solubility product means how easy the salt get becomes ions and gets solvated and becomes ions in water. So the solubility product for potassium fluoride is 11,000. It's really high compared to ammonium fluoride. So it means that for ammonium fluoride and 10 mole of ammonium fluoride, there is still 1.6 molar of undissociated ammonium fluoride. So this is an equilibrium process. At 10 molar, there's still a bit 1.6 molar of this undissociated ammonium fluoride in the solution. So we hypothesize that the reaction goes like this. In the presence of this undissociated ammonium fluoride, well, it helps in the reaction. So the reaction goes by first you have the fluoride anion coming to form a bond with the aluminum. So after forming this bond, then this aluminum titanium bond should break, but this titanium would then need to grab to form another bond, and it forms another bond by grabbing a hydrogen from this undissociated ammonium fluoride. So in doing so, yeah, you get you produce ammonia gas. So this is a pretty interesting. In a way, we try to figure out what's going on in this etching process. Yeah. Well, so interesting chemistry aside, we show that we are able to produce MXene that is of high quality. You can see that when we use it in supercapacitor, it has a performance comparable or even better than what's reported. So this goes to show that the MXene that we produce is yeah, pretty good. Excuse me. So I think I'll just go pretty quick with a few other examples in energy storage. So the same brilliant student Zhong, he went on to use the MXene in this lithium sulfur batteries. So he makes the MXene that he produced with the lanthanum precursor to form lanthanum oxide, and mix it in PEN polymer solution, do the electrospinning and produce well, the lanthanum oxide MXene hybrid material that is on carbon nanofiber after thermal annealing. So this material shows to be pretty good in lithium sulfur battery, in particularly at 2 coulomb. The decrease in capacity, I think, started from around 900, and after 1,000 cycles, you maintain above 600 milliamp hours a gram. So I think that's the key thing of this paper, making use of MXene and also coupling it with lanthanum oxide to produce a synergistic effect in catalyzing the transformation of polysulfide into the yeah. So to produce this catalytic effect. All right. So the other two examples, I think I won't go through because they don't use 2D materials in here. So in this example, it's just simply a bubbling carbon dioxide gas, and that does wonderful things to the zinc ion battery performance. So if you're interested, just please go and refer to this paper. And the other work that the same student did was employing this water glass. So water glass is just a silicate mixture to form a layer of silicate. So water glass is something that you can buy from Bunnings, so something that's cheap, and it forms a very good protective covering for the zinc anode. Right. So for the electrochemical reactor work, this is something that's still in proposal stage. So last year it didn't get through the EOI stage. So we are trying to propose this again, and hopefully, yeah, we can get some money to improve our packed bed reactor. So it's still going to be a batch reactor, but the thing is, we will then design the flow of electrolyte through this reactor so that the electrolyte can get a better mixing through the packed bed. And also we are thinking of adding electric field into the working electrode to enhance the reaction. So these are just yeah, we haven't got there yet, and this is what we propose to do in future to improve the reactor. So I think just the last 10 minutes, I would touch on the 3D printing part. So as a chemist, it's really easy for us to choose the direct ink writing, because direct ink writing is nothing fancy, not much technological requirement. We just simply put the ink that we want to print into a syringe, and then simply extrude the ink out through a nozzle. So this is simply termed the direct ink writing 3D printing. So this is really easy, but the only tricky part is the ink preparation stage, where you have to blend the conductive filler, the active material, solvent, binder, blend them all well, and then importantly, you have to create a good rheology, the shear thinning rheology for this DIW 3D printing to work. So if you get the chemistry and rheology right, you can then just load it up in the syringe and extrude it, and then create the device that you want. So in this first work, we did that blending the electrochemically derived graphene oxide, EGO, with PDMS elastomer beads. So these PDMS is they are, I think, less than 1 microns. So we call it sub-micro elastomeric beads. And with these beads and conductive filler and also some polymer and water, we formulate the ink that could be printed using the DIW 3D printer. So this was the very first 3D printer that we used, which is really expensive. But you could. So nowadays there are many different types of cheaper direct ink writing 3D printer. So you don't have to really go for the expensive type. But the technology is the same. You load the material that you want to print in a syringe, and then force it out, extrude it out using compressed air. Yep. And so we did that, and remember the unique property of EGO at 200 degrees Celsius, you can control its conductivity, and so that's what we did. We control the conductivity of this nano composite. So this nano composite is the elastomeric bead wrapped around by EGO. So you can control the volume resistivity by the annealing temperature. And this was done at 150 degrees Celsius. So you could get the right volume resistivity that give us the highest sensitivity. So we could achieve sensors that's good enough even to detect the pulse. So the thing that I think I'll just skip this part over here. So the next example we did was to blend the MXene with a surfactant molecule. So this surfactant molecule C12E9 is a liquid, it's a viscous liquid, and we just take this surfactant, blend it with MXene, and then it forms a printable ink. So that's just amazing ink from just two component, and we could print it pretty well with direct ink writing. And in this work, we showed that because of the fact that of the shearing of this nanomaterials through the small nozzle, the shear effect creates the shear alignment of the MXene flakes. So the MXene flakes get shear aligned and form ordered shelves or ordered stacked when we extrude it through the nozzle. And in this example, we could print 1, 2, or 3 layers, and it still maintain or give us a high volumetric capacitance. And we attribute it to because of the alignment of the MXene flake that is induced through this printing process. Right. So I think because of the time, I would do a summary in this area where we are focusing on, that is 3D printing of energy storage devices. That's the DP that I'm really currently working on. And in one component of the DP, we really want to enable this direct ink writing with electrochemistry. So putting in working electrode wires into this 3D printer and try to perform electrochemistry as we do the 3D printing. So that might be something interesting. Yeah, hopefully I can present that next time. All right, so hope I've shown you my work on utilizing electrochemistry to produce the nanomaterials, and also concurrently using 3D printing technology to fabricate a device. And lastly, I want to thank all the students that was involved. Basically, all the work that I've presented are done by the alumni, the students and the postdoc. And my current team is pretty young. So these are the members, I will say, after COVID. And then these are the ones before COVID. Well, they are both equally hardworking and contributed all to the output of my research group. And of course, thank the funding agency. And lastly, yeah, thank you for your time. And please do visit us at Brisbane or Gold Coast. Yeah, thank you. Yeah.
Thank you, Yulin. That was a fantastic recount of your journey, starting from your initial discovery in a postdoc of electrochemical exfoliation, and then taking it through to scaling up, challenges in scaling up, and then coming to real life devices. So I think for students and postdocs, this is a real good example of thinking about how to build a research career. So thank you, Yulin, for your wonderful talk. I think we don't have too much time, but maybe I can ask 1 or 2 questions and then leave it to the audience, another question probably for the audience. Now, you mentioned that your EGO was reduced very easily at about 200 degrees centigrade.
Yep.
Can you tell us why that is the case? Because, in general, all the oxygen groups you think about require higher temperatures than 200 degrees centigrade.
Yeah, I think that got to do with the oxygen functional group, because you could see that from XPS, that's a slight difference. Yeah, I think from the XPS, you can see from Hammers, the GO, you get quite a lot of carboxylic acid. And for our case, not much. It's mostly alcohol, epoxy. And carboxylic acid also got to do with because they are all on the site or on the pores, on the holes. That's where you find the carboxylic acid. So probably for EGO, there's less defect, less hole defects. Yeah, and so we're guessing that it's because of this functional group that's more thermally labeled.
I guess we have time for 1 or 2 questions from the audience. Please raise your hand if you want to. Questions? Maybe I will prompt another question, Yulin. So when you do these electrochemical reactions, I just want to kind of mention that I think First Graphene is probably one of the companies which makes graphene by this sort of electrochemical reaction now. But that aside, I just want to understand how do you manage the counter effect of flaking of graphite flakes in all these reactions? Because if you do it on a scale, that is probably one of the biggest challenges you would have, right?
Yeah. So that's why we make use of this mechanically assisted reactor. So that was a way we can use flake graphite, and also with the pack bed, the pack bed design where we could pack the graphite flake, and then but of course this is the batch reaction, so we need to allow sufficient time for it to get well oxidized. Yeah, so I guess the drawback in this would be the time required to really exfoliate and oxidize the graphite into graphene oxide. So I'm not too familiar with the first graphite the product that they produce. I don't think it's graphene or graphite oxide, right? It would be just few layer few layer. Yeah.
So if I go back to your the what is called as a basket reactor, the reactor you showed with the titanium mesh.
Yeah, that was the work done at Monash.
Kind of. Yeah. That is usually called in a reactor technology, it's called a basket reactor.
Oh, yeah.
Now, I'm just wondering, when you are exfoliating the graphene from graphite, how do you ensure that you are collecting the exfoliated product versus the flaked off products? Because you may have so is there a density difference or some sort of separations?
Yeah, I think in this paper, what we did was very simply just take the whole thing and then wash it, and the graphite would and then disperse it in a large amount of water. So of course the graphene oxide will be well dispersed, and then the unreacted one will be at the bottom. But that's very tedious and wastes a lot of water.
Thank you, Yulin, for clarifying this. I knew this work was happening at Monash when you were here, but kind of haven't followed it up. So thank you for your clarification.
Yeah, that was one of the reasons why we had to change to the pack bed reactor.
There is one colleague of mine at Texas A&M, Micah Green, who was kind of doing some of these experiments for electrochemical exfoliation. He's an engineer, so he probably designed some systems where you could kind of separate the exfoliated versus non-exfoliated components a bit more easily. I've not followed up the work, but I know that he was doing some of these activities. Micah Green at Texas A&M.
Oh yeah.
You must know this name. Anyway, any other questions from the audience? Otherwise, we probably have to say thank you in a few minutes. Has anyone raised hands? All right. So, Phil, do you want to say the final thank you?
I can.
All right.
Thank you, Yulin, for your talk, and thank you to the audience. And Yulin, we look forward to seeing you down here in Melbourne sometime.
Oh yeah, right. Yeah. So I guess there's you guys need to come and see the work before they can ask questions. So do welcome everyone who has can come down to our lab in Brisbane to take a look and potentially have some collaboration. Yeah.
Absolutely. Thanks. We will when I visit Brisbane, I'll probably check in at your place.
That's great. Sounds good. Thanks. Yeah.
All right, guys. Thank you, everyone, for your time. I think that was a good talk. I think it is recorded and will be available if Yulin agrees on that.
Sure, go ahead.
It's just so we'll put it online for people to review and look at the publications a bit more intently. All right. Okay. Thanks, everyone. I'll probably see you soon on another of these Talk2D versions. Thanks.
All right. Thank you. Thanks.
Everyone.